Hello, my name is Chao. I am a PhD student from University of Illinois. Today I am presenting our work, Koord, a language for programming and verifying distributed robotics applications. This is a joint work with my colleagues in UIUC, Ritika Ghosh. She's a former PhD student, and Professor Sasha Misailovich in Department of Computer Science, and Professor Shah Mitra in the Department of ECE. To start with, our work is motivated by the wide applications of multi-robot systems in recent years. As we can see here, Roombas have been used in transporting inventories in warehouses. In agriculture, there are researches on using small ground vehicles for surveillance, disease monitoring, and weeding and farming. We've also seen plenty of drone shows. And finally, there are drones being used for medical and package deliveries. However, designing and building a reliable multi-robot system remains challenging. This is because it involves reasoning with two very different types of concerns. First, the correctness concern in coordinating multiple robots has to deal with inherent concurrency and asynchrony. These are intensively studied in the distributed computing community. At the same time, we also have to ensure that robots correctly interact with the physical world under noise and disturbance. The control theory community has put decades of studies on these topics. Our goal in this work is to investigate if there is a clean abstractions so that we can achieve separations of concerns and we can reason each correct concern from different community with the existing techniques in that community. Our main insight is that it seems the correctness argument for the distributed coordination will be the same regardless of the vehicle platforms. That is, these correctness arguments should be platform independent. And it can be separated from platform dependent concerns such as motion control and sensing. To give a more concrete example we study in this work, let's look at this simple delivery problem. Suppose we're given a set of tasks specified by their locations and set of robots. These robots are required to collaboratively visit each of the delivery locations exactly once, while avoiding colliding with each other. This kind of problem can model, for example, delivering or scanning an inventory in the warehouse. So what does an approach to solving this problem look like? A simple approach might look like this. A robot starts from looking for an available task. On finding such a task, the robot checks whether it has a clear path to it. In this case, it is blocked by another robot. Then it looks for another task. If this task has a clear path to it, then it shares its planned path with the other robots and start to follow the path. While following the path, the robot will check if it reaches the task location. Upon reaching the location of the task is marked complete and removed, and the whole process repeats until there are no more available tasks. We can roughly see the upper part of the flowchart is when a task is assigned to a robot, and the lower part is when the robot is trying to complete the task. This is a fairly simple design. So what are the problems in implementing this application? This straightforward design, however, requires several building blocks. Checking the availability of a task amongst robots actually requires mutual exclusion between robots. Finding a clear path to a task actually requires sensing and path planning. Following the path requires path following control. And sharing paths with other robots requires reliable communication. Each of these topics is a challenging research problem by itself and is studied in decades of research. Ideally, the programmer will want to focus on only designing the high-level algorithm of this flowchart. And this flowchart is platform independent and should work with any vehicle that provide a proper abstractions on its path planning and path following. So in our work, we design this high-level algorithm using our programming language Koord. And the platform-dependent controls are abstracted as controller ports. And we choose distributed shared memory for communication. Here shows the Koord program that implements the high-level flowchart. I'll skip the detailed Koord syntax and only highlight some language features. So there are two events, assign and complete, which correspond to the two parts in the flowchart. And then there are shared variables for sharing tasks and path between robots. There are also controller ports for sensing the position, for detecting whether it reaches the target, for path planning, and also for path following. Finally, there are some local variables. So the code is quite concise and encodes the logic we see in the flowchart pretty closely. And I want to mention that this exact same Koord code for delivery application is compiled and actually deployed on real drones and cars in our intelligent robotics laboratories, and also provided in the simulation engine. So it actually shows that the Koord language is indeed realizable and portable onto different platforms. Besides delivery application, we're also able to create a formation flight application using Koord. So if we look at the textbook algorithm, it is really succinct, and it is because it assumes the robot has access to its neighbor's positions. In Koord, robots can share their positions as well using the shared memory, and we can see that this Koord code is also very succinct and quite close to the textbook algorithm. And on the right, we can see the algorithm being simulated in our simulation environment. And the third application is to collaboratively create a global map by sharing its local map with other robots. In this application, it is required to design and implement a new controller port for the LiDAR range sensor we've seen here in the simulation. Again, once we have the proper implementation for the controller ports, the Koord code is quite concise and actually readable. Now we discuss the formal semantics for the Koord program. First, we discuss the configuration of the system. In the previous slides, we see that a Koord program will have local variables, here the local memories, and sensor and actuatable as controller ports. And we also have an additional field called terms that basically says whether the robot is executing statements inside the events or following dynamics. but this is only a robot configuration for one particular robot. The core program actually runs on multiple robots. So the system configuration actually consists of the robot configuration of all the robots. And there is a global shared memory for communication between robots. And in addition, we also assume a global clock tau. The execution of the Koord system is round-based. Each round is divided into program and environment turn transitions. In program turn, each robot will execute an event transition. Once all robots finish the program turn, the system enters the environment turn. And each robot interacts with the environment and updates controller ports and goes to program turn in the next round. We have formally specified all these transition rules in our paper and in Koord semantics framework. Now, to ensure certain safety, for example, no two robots collide in the delivery application, we can specify a predicate phi that any two robots are never too close. And we would like this predicate to hold for all reachable configuration in the round, and that is, we want to prove it to be an invariant of the system. Following our semantics, we can decompose the reasoning for invariant over configurations in the round into reasoning with configurations in program terms and in the environment terms separately. In program terms, we're able to use symbolic execution provided by K framework to reason with each statements in each of the event transitions. For reasoning with configurations in environment term, we encode the physics as a function of controller ports and time. This function can be an explicit dynamical system, such as in the differential equations if we know exactly the environment model. Or it also can be a black box simulation or execution model. Note that we would like to prove phi hold not only for the beginning and the end of the environment term, but we also want to prove it for all intermediate configurations reachable between time tau to time tau plus delta. To reason with these intermediate reachable configurations, we're able to reduce it to the reachability problems for dynamical systems. That is, to over-approximate sets of reachable configurations. This is a well-studied problem for dynamical systems, and it has plenty of existing approaches. In our work, we use a tool called Invariant that supports black box physics model and does not require a complete dynamic model. And in our work, for example, we are able to use Invariant to prove our drones staying within some bounded area on the left. However, the car may not stay within the area because it may overshoot when making a right turn. To conclude our work, we propose Koord, a language for distributed robotic applications. It allows clean and concise programming, and the Koord program is implemented and can be deployed to real vehicles. So Koord follows this principle of separation of concerns. It allows us to follow really rigorous formal reasoning on the correctness of a Koord program, and our decomposed verification approach helps us avoid reinventing the wheels and is able to use existing tools for verification. Finally, I would like to give a shout out to our members in the Sci-Fi House team that helped realize and deploy Koord programs and design the simulation engines. And Also, I would like to promote our project. Our information and implementation for Koord can be found on sci-fi-house.github.io. If you're interested, feel free to contact me through the email. Thank you.